recording?
Okay. It started.
Okay, awesome. Thank you very much. So it's my pleasure to welcome Dr. Ramtin. He's associate professor in University of California, Santa Barbara in EC department. He got his PhD in UC Berkeley. And basically before that, he obtained his master's in EPFL in Switzerland. And before that, he got his undergrad in Tehran in 2009. His research includes machine learning, optimization, information and community theory, stochastic networks, and many other things. He also obtained like many different prizes, the best paper in IEEE International Conference on Communications, 2014, also additional paper award 2020 from Computation Information Theory Society. And today we'll speak about personalized federated learning, how you can make it fast and robust. Okay, please.
Thank you. Thanks for the nice introduction and thanks for having me. It's a pleasure to be in UAE and at English AI. And I'm actually quite impressed by my visit already. So today I'm going to talk about federated learning. As we will see, it's basically a setup that we want to learn a machine learning model from multiple users' data. But there are challenges in terms of speed, in terms of robustness, in terms of data distribution, and so on. So in this talk, I'm going to address some of these challenges briefly, but I'll be happy to talk about the details more offline. And as you mentioned, I'm at University of California, Santa Barbara, which has a weather quite similar to here in summer. So winter here is like summer in Santa Barbara, but other seasons we always have essentially spring. So if you like to visit, let me know, and it's a nice location next to the beach. So let me give you a brief background. Traditionally in machine learning, what we want to do is basically collect a lot of data. Let's say this data is collected at a data center, Google's data center, Amazon data center. And we want to learn a model. So this model can be, for example, face recognition application. What is the issue with this? So for modern applications, there are a couple of issues that can be difficult for gathering all this data in a centralized location. One issue is continuous communication. So if this data is gathered at the edge nodes, like mobile devices, continuously they should be sent to a data center, which is a huge communication. A more important issue can be privacy, right? So we want our data to be kept local, and we want that to be private. But if we just send it to a data center where the data is gone, as soon as the data is revealed, you cannot really assume that privacy is guaranteed. So because of these issues and other issues, just in terms of computational power, we have all these mobile devices, all these edge nodes that already are like a distributed computing system for us. So why not using it for learning the machine learning model directly? Why should we do the computation at the center? So because of these issues, we are actually moving towards ML models that try to do edge computing, try to learn these models at the edge. And federated learning is actually the paradigm that tries to do this. Okay, it's federated, it's distributed, data is gathered at mobile nodes, edge devices, IoT devices, you say it, smartphones, and they are processed there, but they will be coordinated with a central. Now, let's do a more accurate comparison. So in centralized ML, we have this data. So here we have image classification. And this data will be all sent to a master node or a data center. We are going to have some learning algorithm, like maybe using stochastic gradient descent. And the issue is lack of privacy, high communication load, and also slow training because we are using the computation power of one server or probably multiple servers, but at one location. Federated learning, the idea is that this learning algorithm will be implemented at the edge nodes. So let's say at some iteration, the current learning model will be shared with these mobile nodes. Then we are going to have an update, again, maybe using stochastic gradient descent. And these results will be aggregated, uploaded back to the parameter server, to one central node, aggregated, and this iteration continues. Okay, so this is kind of the architecture of federated. So everything looks nice, lower latency because of the computation power of the nodes, smaller communication. It's more privacy preserving because data remains local, less power consumption, and we are gonna have smarter models because we can use more data. Okay, we can have millions of IoT devices and use all that data, so we are gonna get smarter models. And this was first introduced by Google, and there have been many, many papers on that. So I'm not referring to this large body of literature in the talk, but there are a lot of works. And Fed average is the algorithm I just explained, basically, which tries to solve this, first introduced in this 2017 paper. And if you are interested, there are nice survey papers that you can go to. So everything seems fine, but there are issues. There are issues that I'm going to talk about in this talk, some of them, but many of them remain to be solved. So one issue is system heterogeneity, we call it. So remember the architecture that I explained, there is this synchronicity issue. That's okay, the nodes have to do the computation, send back to a central node. Now, if one of them is a straggler means a slower node, or breaks in the computation. So the whole procedure will slow down. Okay, so this we call system heterogeneity. Another issue is data heterogeneity. Data heterogeneity is about non-IIDness of the data. So in a typical ML problem, you want your data points to be IID to learn a common model. But if they're not, here you need to basically have a model, have an understanding of this non-IIDness. If it is like arbitrary, why is it even useful to do learning? Like you won't do learning on images that are totally unrelated, okay? So there is definitely a relationship that has to be modeled, but there is also not exact IIDness. So how can we handle this in a federated setting? And on top of this, we may also have the issue that each user prefers, because the data distribution is different, prefers to have a different model. So for example, the text messages that I send, they have a particular distribution. So the next word that should be suggested to me is different from the word that should be suggested to Sam, right? So it means that we need two different learning models. This we call personalized federated. Communication efficiency is still an issue because it's an iterative algorithm. So in many rounds, these updates are done. These models are typically huge. Think of the edges of a big neural network. They have to be sent to a parameter server in many iterations. And finally, privacy is still an issue. So you may think, okay, data is local, so no privacy leakage, but it's not the case because the gradient update itself can reveal some information about the data. So we need to be careful about these issues, try to tackle them in our algorithm. And we have works that cover different aspects of these challenges in our group: system heterogeneity, data heterogeneity, personalization, and so on. In this talk, I'm going to focus on first system heterogeneity, the straggler problem that I mentioned, some nodes are slower, and then data heterogeneity and personalization. So what I'm going to talk about is like one approach of tackling. As I mentioned, there are many papers out there different approaches, all of them interesting, and it's application-based, which one is more useful. So just to put some notation and go to the straggler problem, let's revisit the Fed average algorithm. Okay, so in Fed average, we have at iteration k, model WK sent to the users. Then we are going to have tau rounds of SGD. Okay, why tau rounds? Why not one round? Because of communication efficiency. So we want to do more work at each node before synchronizing. This is more communication efficient. So tau rounds of SGD, and then we are going to have WK1 up to WKN and users. This will be sent back to the master node and averaged. Okay, this is going to be the next model. This continues. Very simple algorithm, just a useful algorithm. Now, suppose that this second agent, this second mobile node, is much slower in the computation. So these tau rounds of computation will take maybe, I don't know, I'm going to put some random numbers, 10 seconds for the second node, but 1 second for the rest. Now the whole algorithm iteration in this iteration will take 10 seconds to run. But it was supposed to be 1 second because of some maybe hardware issue at this node. Okay, straggler issue can be due to different reasons. Maybe most of the phones are new iPhones or Samsung, whatever, new phones, but one of them involved in this procedure is an old phone. It's a hardware issue. Another possibility of straggler, the communication channel between the second node and the master node is much slower, and possibly other reasons. So this is called straggler. And a federated network consists of thousands of devices typically. And they have a variety of computation, communication, and storage capabilities. So do we have a question? Okay, so because of this, we are going to have slow training and possibly unexpected delays due to stragglers. Now, how can we address this? So our key idea here is that basically these stragglers, there is a reason for them to be slow. If it's a hardware reason, as I mentioned, they are always going to be slow, okay? If it's a communication channel issue, maybe they're not always going to be slow, but it's more likely that in multiple rounds, they will be this slow. Okay, so it's not that this straggler, in many words, you see a random model, like each user at every iteration is a straggler with some probability. I don't think that's a good model because there's a reason that if my node, my phone is a straggler, it's more likely to be straggler next time as well. Okay, so we have this philosophy, and based on this, we want to mitigate this issue. Existing approaches, there are different ways of doing this. You can just ignore the straggler. What is the issue with this? The issue is, as I said, this straggler remains to be straggler in every round. So ignoring that user means not using the data of the user. So you lose accuracy. That user may have very valuable data, maybe actually, for example, a distribution which is among the minority distribution that you want to use. Okay, so there are fairness issues here. Asynchronous training you can use, but it breaks the proof of the system, it breaks the convergence rates. In many cases, it doesn't work well. In some cases, it does work well, so it's application dependent. Our approach is to leverage basically interplay between statistical accuracy and system heterogeneity. So by that, I mean each user, let's say, has 1,000 data points. Okay, there is a statistical accuracy that the data of this user can hope to reach. Okay, once you reach that, the contribution at this point is done. Okay, you need new data. So this kind of basically inspires us to think about, okay, how about starting with fast nodes, reaching their statistical accuracy, then adding the slow nodes. We want all the data to be included because they have useful information. But let's start with the fast nodes, and in next round, in future rounds, include the slow nodes. And what is the optimal way of doing this? What can we prove? What can we show in terms of speed? So the algorithm that we develop is called adaptive node participation approach. Okay, so adaptive node participation, it adapts to the statistical accuracy and speed. It's very simple actually. Let's say we have n heterogeneous devices and we sort them by speed. Now you may ask, how do we know which node is faster and which one is slower? It may be time varying, and you are right. One way to approach this is to have, in communication theory, we do this actually. We have like a preamble or a few rounds of probing basically to see the response time of these nodes. And if we assume that the time varying aspect is slow enough, we can do this probing every now and then. Maybe after every 100 iterations, we do a new probing. Okay, but for mathematical simplicity, we just assume they have a fixed speed and we know it. Okay, so we sort them, fastest to slower. Then what we are going to do is we start with a fixed number, let's say n naught, fixed number of fastest nodes. We do federated learning on them. We do it until we reach the statistical accuracy. Okay, and this we can formalize mathematically. If we keep iterating on these three fastest nodes, it won't be useful at some point. We may get basically better training error, but in terms of test error, generalization that we care about, it doesn't improve any. At that point, we need new data, we add a batch. So we double the number of participating. And we do this geometric increase that we can show that it is actually order optimal. Okay, so we do double, double, double until everybody is included. Even the slowest nodes, this way we can reach the optimal statistical accuracy. And the point is, the initialization of this set of users in the second round will be the train model of the first round. Okay, so we continue this until we include them. The algorithm is simple. Let's see if we can analyze this. So we have a typical ERM empirical risk minimization. For analysis, we have IID samples here. Okay, for mathematical purposes, n nodes each has S samples. We have expected risk, we have empirical risk, and we know from results in the literature what is the statistical accuracy that we can hope to get. So basically, the difference of empirical and expected risk is basically upper bounded by O of 1 over n total data. So if we proceed more than this, it's not useful. Okay, once we reach this, we can double the number of participants. So the algorithm is, as I explained, and the way we can implement this is you can either do it with a heuristic approach that you see the improvements are getting smaller and smaller, or you have a good measure of this constant V. It depends on like smoothness and parameters like number of data and so on. Typically you do it kind of in a heuristic way, but mathematically, if we want to prove it, we assume knowledge of it. And then we implement the algorithm. One thing I want to mention is that this is a modular approach. So your federated learning algorithm can be the algorithm of your choice. For example, Fed average or Fed gate. Here for analysis, we use Fed gate, which I'm going to talk about. The reason is that this meta algorithm for straggler issue is really saying that first few rounds work with these nodes. Next, work with double of this stuff. Now, in that round, whether you want to do tracing of a gradient, you want to do just simple Fed average, it's your choice. So what we can prove is if we use Fed gate, which is by the authors mentioned bottom of the slide, we have optimization guarantees. So the assumptions are standard. We have basically condition number kappa, and we have these results from statistical accuracy. What we can show is that if you use this adaptive node participation with Fed gate, we can actually design number of rounds and number of local updates that we need, and show that we reach the statistical accuracy, the optimal statistical accuracy. But our original goal was time, right? We wanted to do it faster. So to do an analysis of that one clock time of the algorithm, we need a model on these random variables T1 to Tn, which is the computation time. So if we adopt this exponential model, so these are IID exponential from 1 to n, but once realized, they are fixed throughout the procedure. Then we are going to get order 1 over log ns. Ns is total number of data points across all nodes. Improvement in overall computation time. Okay, and just to give you a hint on the analysis, it's basically understanding order statistics of this exponential that we know very well from probability, and kind of comparing the computation time of, let's say, not using FLAMP, just simple Fed gate, which has to wait for the slowest node every round, with what we are proposing. Okay. So of course, if you use every node in each round, the number of rounds is going to be smaller, but the time of each round will be large. If you just use the fastest nodes, the statistical accuracy will not be optimal. This is a basically balance between the two. And we can look at some numerical results for this part of the talk. There are other interesting approaches, FedNova, for example, that tries to address stragglers. So you may also think about this. One way to address stragglers can be the slower nodes do fewer rounds of computation, which is also a good algorithm. It doesn't give you optimal result. We will see here that indeed our algorithm achieves the best one clock time. And an interesting comparison is shown in this plot in terms of basically choosing also just random or fastest nodes. So if you just use fastest nodes, you can see in the picture that the convergence time is very fast, but it does not converge to the smallest possible accuracy, which is the optimal accuracy. These are expected. And this plot is showing that we can use this meta algorithm with different solvers, Fed average, Fed gate. So I think with this, I'm gonna, wait. So with this, I'm gonna finish the first part of the talk. It's a good time to ask questions. Yes?
So I have one question about this average. So for FLAMP, is if you actually know what is the distribution of times, is it always optimal to increase like number of participating nodes by a certain factor, or do you think you can kind of adapt it to the distribution?
It's an excellent question. So the factor to the number can be improved. So it's not optimal. You are right. In the sense that the constant is not optimal. However, the geometric increase, we can show it's optimal. So maybe instead of factor 2, it's optimal to do factor 2.5 increase, okay? And that will give you a better constant. But order-wise, it cannot be improved.
And is this with respect to assuming that the times are, the distribution of the times is exponential?
I believe that this can be extended to, our result is yes for exponential, but I believe it can be extended to a much larger family of distribution. And basically what you need is this order-wise difference between order statistics of the random variable. So if, for example, your random variables are, let's say, bimodal, it's either 1 with probability half or 2 with probability half. Definitely doubling or any geometric increase doesn't make sense. You should include in some rounds all the fast ones that have speed 1, then include all the slow ones that have speed 2. Anything other than this clearly is not optimal. But if you have some sort of, I think it's more than exponential, so it's a good question. But if there's a kind of tail to the distribution and this order statistics that's basically order-wise are different, then our approach is up to constants.
Very stupid question, but when you assume that this is straggling nodes, right?
Yes.
The theory relies on IID. So in your IID, why don't you just ask all of them to participate and just keep the first K responses?
So very good question. So there are, if only, because the IID random variables, they are not realized every round. It's just realized once, right? So it's like first time, let's say we have 4 nodes, each will sample from exponential distribution, we'll get a number, that will be the speed for the whole procedure. Okay, now if I pick the fastest 2, the data of the slowest one will never be used. That will cause bad statistical accuracy. So the learning model will not be as good as using 4 nodes.
But I sound for something else. Imagine you have these 2 nodes, right?
Yes.
And you say, I want to extend to more. Okay. So you can say, hey, now everyone just try to participate. I will take the first K responses. And then somehow maybe try to include those nodes into my core, then optimize in this setting. And again, you can ask everyone, hey, participate. I will try to keep the K fastest. I don't know.
Okay, so the point is exactly here. The K fastest will always be the same K.
Because in your case, you say, I will start with the fastest, and then to include more,
yes,
some slower one, but not the slowest one, right?
Yes.
And then include more and more and more. So maybe you can take it offline.
Sure, yeah. So the key is if you always stick to the fastest node, some people will never participate, bad statistical accuracy. If you always include everyone, slow.
But some for you say, I will take the K fastest, and then slowly say, hey, now you will need to be in my core. And then the same way as you are extending, you start with a small subset which are the fastest, then include it with slower, more slower, and so on, right?
Yes.
So in some sense, you need to make the rule that, hey, at some point, I want to have everyone participating.
Yes.
So increase the time, but early on, I want to maybe just, I don't care about who will give me answer, right? Also, you don't care who gives the answer at the beginning, at the fastest one, right?
Yes. So it's actually what we do here, yeah, basically, yeah. Thank you. So if there are no more questions, okay, go ahead, yeah.
So do you actually have, did you think about extending it to like a heterogeneous setup where you kind of know what kind of heterogeneity you do. And
You mean data heterogeneity?
yes, data heterogeneity.
Yes,
Yeah.
yeah, we tried that. So we can do it. Actually, we have sent a paper that can address both data heterogeneity and system heterogeneity. I had it in my slide, but it is based on representation learning. So it's structured data heterogeneity. Okay, so we can talk offline, but basically the idea is that you are gonna learn, let's say, the representation learning is such that you have a common part for every node and just the last layer which is different. And this way is exactly the same procedure. As I say, it's meta algorithm. So it sits on top of the representation learning algorithm that you use for your heterogeneous federated learning. Now, if, for example, you address data heterogeneity by clustering, let's say, again, you can implement this on top of that, like for every cluster. So that is, I think, the kind of advantage of this method, that since it's a meta algorithm, it can basically, it can be added to your favorites depending on your application heterogeneous algorithm. Yeah.
So question here, like when you have data heterogeneity, maybe also having one node is not the best thing to do.
Exactly, and this is the next part of the talk. Yeah, so it's a great question to kind of bridge to the next one. So here, as you mentioned, so data heterogeneity is a very vast area, and many different algorithms are proposed. And I think for different applications, also different algorithms are useful. So in next part of the talk, what we want to do is kind of look at structured heterogeneity, which is also related to adversarial ML. If you are familiar, I'm going to explain. And see what we can do in the worst case of heterogeneity in some sense. So our motivation is this. So we all agree heterogeneity is important, and we know Fed average doesn't work well with heterogeneous data. So in this part, we are still interested in one model. So it's not personalized. We have heterogeneous data. We want one learning model for everyone. And the reason, so here we argue that in this case that we need one model, data heterogeneity is structured and is device dependent. So for example, we want to do image classification. All the mobile nodes have same type of images, okay? However, the difference in the distribution is because of the different cameras that the phones have. Different brightness, different angles. So this heterogeneity is device dependent and is structured. And more specifically, all the samples basically in this application on a device undergo the same distortions, brightness, intensity. So the way we model this is that we have a common distribution, a model distribution, features, labels. And for each device, the label is fixed. The feature will go through a transform. Okay, this transform can adjust for brightness, can adjust for noise, can adjust for intensity. And the simplest transform that you can imagine, we are going to consider. What is it? It's just affine transform. Okay. So user I, we are going to have affine transform, basically a perturbation, and this matrix which will be multiplied by the feature. And these are common, these are specific per device, but different across devices. Now you can see the relationship to adversarial ML. Just think of lambda to be identity for now, no lambda. This is actually assuming each device is having data points perturbed, but universally perturbed. Okay, this is the device-dependent change in distribution. And these perturbations, they cannot be arbitrary, okay? Otherwise, basically any vector x, you can map it to another vector. So these perturbations should be small to make sense. And small means delta, norm of delta is small, and the difference of lambda and identities. We use for Frobenius norm and just M2. So this is the connection to universal adversarial perturbation. Now, we want to learn this model, machine learning model, one model, using data of everyone, assuming such transformation exists underlying the distribution, but we don't know it. We don't know lambda, we don't know delta. And we want to guarantee for the worst case, okay? For the worst case, the reason is that maybe your learned model will actually be used on a participant or a user that didn't participate in the training phase, okay? If user will later use your learned machine learning model, but still with the same structure of data. So we want it to work for the worst case performance. Means what? Means we have min max for our empirical risk minimization. The minimization is the same as before. Minimize empirical risk. But this time max over worst case of possible lambdas and deltas. Of course, satisfying the norm constraints. And this term, the empirical risk minimization term, the empirical loss, now is over the transform data. Okay, so we want to solve this. Now, at this point, the problem is just an optimization that we want to do. But the challenge, and we can solve this, we know how to do min-max typically in a central node. It's not hard to do min-max. But the challenge is, can we do min-max optimization in federated setting? Federated setting, remember, has to be distributed, has to be communication efficient, which means we need to have multiple SGD, or here we are gonna have ascent also because of the maximization. So multiple iterations before coordinating with the master. So does min-max solvers work in a federated setting? And it should be also computationally efficient. We cannot solve the maximization completely per node because that's computationally heavy. So the question is, can we solve with low computation, low communication cost this problem in a federated setting? And you can think of the algorithm already probably. We do Fed average. What is Fed average? Is multiple rounds of SGD and average. Now we have min max, so we need gradient descent and ascent, multiple round of descent because of communication efficiency, and then aggregate. So the question is simple now. Does this work theoretically and numerically? Okay, so we show that it does, and we call the algorithm Fed robust because it's based on robust optimization. So now, how do we do this? First, we basically use Lagrange multipliers to bring in the objective function, these constraints. Now we have a global loss with a minimization variable W and bunch of maximization variables that include lambda and delta for different devices. So the robust FL framework is the min-max of this function, min-max. And the solver, which we call Fed robust, is just gradient descent ascent. However, there is one important point here, which is the ascent step is per device, okay? So the ascent step, the gradient ascent, which is done over lambda and delta, it only needs to be done once per round of communication. However, the descent SGD similar to Fed average. Because of communication efficiency, we want to do this tau rounds. So tau local updates per round of communication. So the algorithm is, we have the new model double, and the other important thing is that the maximization variables don't need to be communicated to the master. They remain local, so it's communication efficient. Same as before, WT plus 1, the new one, or WT is sent to the users, which is averaged. Now using that, we are gonna have the gradient ascent steps. Then we are gonna have tau local updates, aggregated again. Now you can think that, okay, this is two separate problems, maximization and minimization, because maximization is per node. So why is it hard? The reason is that every time that W gets aggregated, it couples this maximization with minimization. So the next step will be done with the new aggregated W. The good thing is that we can prove it works. We can prove it works. And this is federated gradient descent ascent with low computation, low communication. But what we can prove is under some standard assumptions. So we need bounded non-IID degree. This is commented in the literature. So non-IIDness cannot be arbitrary. We need the SGD to be unbiased variance bounded, also common. We have local functions that are basically smooth, and then we consider two cases. So PL condition is a weaker condition compared to strong concavity, strong convexity. If you are not familiar, just think of strong concave and strong convex cases. So we have two possibilities. The maximization, because of the form of it, okay, it is definitely strongly concave, and of course PL as well. Okay, the minimization may be non-convex, maybe strongly convex. Neural nets are non-convex, like logistic regression is strong. So this min-max problem can be either strongly convex, strongly concave, or non-convex, strongly concave. Or here we do either PL-PL or non-convex PL. And we do have results for both cases. So the way we do the proof, I don't want to spend too much time on it, but it's based on the Lyapunov function, which has two terms. This term is measuring the gap, optimality gap, basically for W. So the distance of W bar with phi star, which is basically using W star, but fixing the maximization parameters. The second term is essentially the optimality gap for the maximization variables. It's fixing W bar and looking at the difference of where we are at now with the optimal. So this we show is decreasing, and we can compute the rates. So the equation looks a bit ugly long. But if we set all the step sizes correctly, for PL, we get log T over T. For non-convex PL, we cannot show optimality, of course, but we can show convergence to a stationary point under 1 over root T. So these are results that we have for minimization only, up to log factors. We can now show it for min-max in federated system. And we also have generalization results, and we can relate the formulation that we have with Lagrange multiplier and so on to the Wasserstein distance of the distribution, but I'm going to skip this in the interest of time, and let's look at some numerical results. So in the right plot, here lambda is identity. So it's actually similar to adversarial ML. We have lambda equals identity, delta, which is varying on the x-axis in magnitude and in norm, and then we have accuracy. So what are the competitions that we may have? One is just Fed average, which we expect not to be very good. And you can see that it doesn't work when the perturbation is large. The other possible competition is distributed PGD, distributed projected gradient descent, FGM. So these are adversarial ML algorithms that we can run in a distributed fashion. What is the difference with our algorithm? The difference is that they fully solve the maximization each round. So think of the min-max instead of, when I say federated friendly, low commutation is this gradient descent ascent that I explained. Instead, you can say, okay, just do Fed average, but each time solve the maximization fully per node. That is distributed PGD essentially. Performance-wise, they are the same with our algorithm, but computationally, we expect to be much faster. So it's federated friendly. Left plot, we are actually having also a lambda, which is not equal to identity. So we have affine shift and this transform lambda. And we again see that Fed average is not doing well at all, but we are comparable or we are actually better than distributed PGD. So with this, I'm gonna go to, I guess very quickly, I'm going to present the personalization part, but I think it's a good time to ask questions about data heterogeneity. Yes.
I would have a question about like your formulation. If you go back to the like the first slide of this
part. Back. Yes.
Yes, here.
Yeah.
So what I was wondering, and I'm missing a bit of a motivation. Like you already assume that there exists like this delta, like the perturbation exists. So why not to frame it as a min-min problem and then compare, like once you have the optimal W, then you would fix the W and compute the robustness with respect to that, like that to solve like a maximization in a fixed W.
Yeah, so it's a good question. So basically you are saying it's actually the formulation related to personalization that we do. You are saying just solve for the minimize over all these parameters. Okay, and these parameters is a model that we have lambda, we have delta. So then the issue is robustness basically that I mentioned. In some applications, actually, you are correct. Probably that is the right thing to do. But suppose that you do this minimization, it only solves the problem for the participating nodes. You agree with this? It only solves, because it's going to actually adapt to, let's say I have 10 users participating. It's going to adapt to their specific lambda and delta. Now you have your model now trained, you introduce a new user, it's gonna perform bad for the new user. Because the new user will have a different lambda and delta.
But can you sound like the users as the hospitals, right?
Yes.
You take the new hospital, you just need to learn the good lambda and delta.
You redo the,
yes.
Yeah, you can do this.
Calibration per user.
So this is exactly the application that, because hospitals, maybe you go from 10 to 11. Okay, so these are the applications that actually probably make sense to do min-min. But if you want to do basically for many users, you may reuse your model in different applications that you may have millions of users, and you are training only on a subset, having some robustness like guarantee like this makes sense. This is one aspect. The second aspect is you may indeed have data heterogeneity, which is induced by perturbation, by actual adversarial perturbation. So in that case, it's clear that you have to do maximization because it's not natural perturbation anymore. It's adversarial perturbation. So suppose you want to do federated learning, However, some users may be adversarial. They may perturb the data point in a way that you don't notice just by delta or by matrix log. Then you have to do.
And also, let's say when you have adversarial, maybe they will always have this delta different, not fixed.
So yeah, it's not universal, you are saying per device. But there are actually, in adversarial learning literature, there is actually a large body of work that studies universal perturbation specifically because it's also harder to detect. So it has its applications. Yeah.
Thank you.
Okay. So let me go to just at a high level explain the last part, which is now we, again, heterogeneous data, but this time we want to have one model per user, as you mentioned earlier, because the preferences are different, so we want to do personalized. And personalization here, again, we want to do it by assuming a structure on a distribution. And there are many methods. So existing approaches, some of them include, for example, we first train a global model and then we adjust it locally. Or we do combination of local and global simultaneously. Or we do clustering. Okay, we do, for example, we can do meta learning. There are many methods. Clustering means you say, okay, this group of users, they have same distribution, this group, same distribution. We do Fed average on each cluster. What we want to do is, the idea is close to the previous one. We again consider a structured model for distribution, but this time we do mean. But as you will see, because of the formulation, the previous results become useful. So this is federated learning based on optimal transport. This is the transportation from a distribution, basically, of the nodes that are different to a common model distribution. So the model is that we have n distributions, P1 to Pn. Then there's this distribution common P that the data from Pi goes to transform psi I and is basically then has distribution P. Okay. Now, if we knew these psi i's, we could basically just transform all the data points, learn the model according to distribution P, learn W star, the optimal classifier. And since we know the psi i's, then we are going to have the optimal classifier for each of these nodes, just by doing the transfer. However, we don't know them. So this time we do mean, essentially. But we need to parameterize these transforms. So think of them, each of them can be a neural network. Parameters theta 1, theta 2, up to theta n. Or similar to previous part of the talk, they can be affine. So each will have lambda I and delta. But the good thing is that it immediately gives me personalization, because I simultaneously learn W star and the size. So we want to do empirical risk minimization, but this time, as you said, we have minimization also over the parameters of this transform. However, how does it kind of relate to the distance of the distribution? We cannot hope to have in our optimization a perfect match to this common distribution P. So we need to have a penalty term. That is Wasserstein distance in optimal transport theory. But this is essentially n-array distance. Typically, we have Wasserstein distance between two distributions, distance of two distributions. Now it is n distributions with a model distribution. We can formulate. Okay, so Wasserstein distance of this according to cost, we want it to be small. We have the transportation parameters, model parameters, empirical risk minimization, and this we can formally define. Basically, in Wasserstein distance, we are optimizing over all joint distributions that minimize the cost and respect marginal distributions. Now we introduce this again with the Lagrange multiplier in our optimization, and this is minimization. The interesting thing is that Wasserstein distance itself is a maximization problem. So to calculate Wasserstein distance, we need to do max. So again, this becomes min-max. It's a min-min formulation. There is no max fundamentally. Previously, we had the maximization because we wanted to be robust. Here is personalized FL, we don't need it. But to compute this, we have a maximization. So this is because it's in our cost, we need to generalize the Kantorovich duality, but I don't want to go to the details. Just take this point that WC itself is a maximization with parameters phi that have a constraint. Okay, so let's accept this. And then going back to previous min-max problem, federated gradient descent ascent, but this time it gives us actually a personalized result. The reason is that we simultaneously learn these parameters theta for transportation and W on bottom. The proof is the algorithm, the proof is a bit different, but essentially inspired by the previous work. And what we can show is that, again, we reach a stationary point if we adjust the step sizes correctly, order 1 over root t, similar to, yeah.
Very stupid question. If you go to
Yes.
the slide.
Oh, sorry. Here.
Yeah, so when you had this like Lagrange, what do you do with lambda?
So lambda has to be chosen basically in a way that balances between these two. It's a constant, and the kind of, it shows up in the constants of the optimization bound. But just you can think of it just as Lagrange multiplier.
Because sometimes you can also think about adjusting the lambda.
Yes, and it will be important for speed of convergence and so on. So yeah, it is very good question. In terms of practice, we just try basically, but in terms of theory, for any constant, it works. Okay, move forward. Okay, so I'm gonna wrap up. We are a bit over time. So we have some numerical results here for AlexNet 100 nodes. Different data sets for MNIST, CFAR, color MNIST. So here we actually have transportations through a 2-layer neural network, basically. So this mapping is a 2-layer neural network, and it is like one common layer. The last layer is different per user, which makes the distributions different. And we see good performance of our algorithm and some comparisons with like meta learning, FedMI. So these are other personalized algorithms. So I should state that since the underlying distribution is using the model that we are considering, it makes sense that we are doing better, but it shows that at least for the applications that you have this mapping of different distributions to a common distribution, this is FedOT is the right approach, federated learning based on optimal transfer. InceptionNet, another numerical result, which again shows strong performance. But let me wrap up. So in this talk, we discussed stragglers first. data heterogeneity, personalization. Other challenges that are important, I didn't talk about today. We have works on our communication load, privacy. And then you can ask about what if we want both data heterogeneous, system heterogeneous, we have a work on that, and also personalized. So these are directions that we are working on. What I'm more excited about these days is basically the economic aspects of federated learning and the interactions that is, or the trade-off that we have when we kind of consider accuracy and privacy and fairness. So I'm going to give you one example to finish the talk. Think of a federated setting that users have different privacy requirements. Now, a person without privacy requirements will provide clean data. A person with more privacy requirements, the data will be noisy. It may be so high that it's again essentially useless data. But we may have a free riding here. Okay, those who require more privacy will also enjoy the final learn model, but they haven't shared their data. Okay. On the other hand, we have the heterogeneous distributions. So distributions that are more common in population will remain more private. Distributions that are less common, they remain less private. So how can we be fair in an economic sense? So if we have a platform, let's say Google, with all these users, can we pay the fair amount of money to these users to incentivize them to participate? How can we make sure they are truthful? So these are interesting future directions that I'm looking at, and I would be happy to talk offline. And with this, I'm gonna finish. Let me just acknowledge my co-authors, Amir, who was my PhD student. Most of this work is his work. Actually, he's now a postdoc at MIT working with Professor Jad Babai. And also colleagues, Hamid and Aryan at UPenn UT Austin. Farzan, who is now a colleague at UHK, at the time was a postdoc at MIT with Ali, and Isidoros, who is a student of Aryan at Austin. Thank you.
We have time for one short question. There's so many questions asked during the talk. If anyone has a question, please ask.
I have one quick one.
There's maybe one question.
No, I think that's it. Okay. Clap. Yeah. So in the last algorithm you showed for maximization, you actually take as many here. So you do not take only one step, but you take as many steps as a minimization. Is there a particular reason that here you actually take as many steps as descent? Ascent and descent are the same. While for the previous approach, you only had one step.
Good point. I believe that there is technical reason for this, for the proof, but in practice, I don't believe it is needed. But I'm not sure. This is a good point. We do take multiple steps. So, yeah.
Thank you. Thanks again, and let's enjoy the afternoon.